It's day 19 of the advent of compiler optimizations. We're going to continue calling and returning and inlining and functioning and all that kind of stuff by looking at tail call optimization. Tail call optimization is when the compiler can do something clever when the last thing that a function does is a call to another function. The way that I'm going to demonstrate that is by writing the greatest common divisor algorithm and seeing what the compiler generates. So unsigned greatest common divisor, unsigned A, unsigned B. You'd thought by now I'd have learned how to type. We're going to say if B is equal to 0, return A, which I think is the right way of doing it. And then otherwise, we're going to say return GCD of B and A modded with B. Okay. What does the compiler do? So we're using recursive definition of GCD, which is the classic way of defining the algorithm. And we've got our terminating case of if B is equal to 0. Otherwise, we're recursing by calling GCD with B and A mod B. So what do we see in our output? First of all, the first thing you probably notice is that there is no call instruction on the other side. There is no push or pop. There is no obvious sign that recursion is going to happen at all. And in fact, recursion is not happening on the right-hand side. Let's read the algorithm through and then sort of work it backwards. So we're checking, first of all, is B equal to 0? ESI is B. If it is not, then we go to L2. Otherwise, we're jumping to L10. So let's assume we're going to L10. If B was 0, L10 says return A. In a slightly more complicated way than I think it ought to, and I'm not quite sure why it decides to move EDI into ESI and then move ESI into EAX. We'll leave that mystery for another time. But that is the if B is equal to 0, return A. Otherwise, we're jumping to L10. L10 sets EDX to 0 and then uses the single argument call to the divide instruction. That takes the register pair EDX EAX, that is two 32-bit registers, this is a holdover from 32-bit days, and treats it as a 64-bit value and divides it by ECX, or ESI, sorry, in this instance. So we're taking 32-bit EAX, 32-bit EDX, and we're dividing it through by ESI, and the results go into EDX and EAX. EAX is the result of the divide, and then EDX is the result of the modulus. So we always get the division and the modulus whenever we do a div instruction. We talked a little bit about this when we looked at our ASCII routine, and we found that there were no divs or mods at all in that, but that's completely different. Here we are cursed to actually have to do a divide because it's with a non-compile time known constant. So, having done that, we say, move some things around, is the remainder equal to 0? If it isn't, then we're going to loop. So at this point, what's happened is that we've inlined ourselves. Now, obviously, we can't inline a function that is recursive because the second call will cause the another inline, another inline, another inline. So that doesn't happen here. The compiler has realized that by having the last thing a function does is calling another function, is that it can now just jump straight to that function. And because this function is in fact the same function, it is like a goto the beginning of this function. And so it's treated it as such. And of course, a goto with an if check is just another loop. And so the compiler has rewritten the whole thing as a loop. And that's what we see. We see like a check and a jump back round. If it's not equal to 0, back up to L11, where we move A into B, and we've already got the remainder in the right place. So that's a pretty clever thing to do. As you can see, it's kind of important that the compiler has in fact turned this recursive function into a loop, because otherwise it would sort of have unbounded stack usage as it called itself over and over again. If you passed in a large enough number, then the number of steps that it was doing through this algorithm would cause the stack to blow out by that many sizes, and that could be a problem. As a result, sometimes it's useful to be able to force the compiler to apply this tail call optimization. And so we can put something like, I think it's clang must tail up here. And I guess as a result of that, I'm going to have to actually use clang 21x86. There we go. And why are you complaining? That's not the right thing. Can't be it to declaration. Oh, where does this go? Oh, whoops. Is it there? I don't know. I should not talk about that. only a return statement. Aha. Okay. It goes here. There we are. Oh, interesting. Isn't it that funny that it makes the code change? I'm not sure why that's going on there, but anyway, you can put this attribute to force the compiler to do tail call elimination, at least for Clang. It would be an error if it was unable to. And that allows you to write algorithms that are recursive in the way that you phrase them, and yet you are absolutely relying on an optimization that the compiler is doing to turn that recursion into iteration through tail call optimization. Now, if you read the blog article that accompanies this particular post, I go off on a huge tangent about why you might use tail call optimization in the context of emulators. So if you're interested in that kind of thing, I recommend you check out the blog article. But if that's not your cup of tea, or if you're already in over your head on this kind of stuff and thinking that I'm already talked too much about branch predictors and other things, which is what the article talks about, then I will see you tomorrow, I hope.